So I usually have these boards and I get to do a related, off topic, but related with this. And I don't have my big chalkboard to like do all my drawings on. I have a blank piece of paper somewhere, maybe. So unsaturated means that we have double bonds or triple bonds. That's as simple as it is. And so these are, double bond means it's an alkene, and a triple bond means it's an alkyne. So there's all kinds of jokes that we make with these. Now back to the question Philip just asked. In the cycloalkanes, they are considered saturated, but these guys here, these are cycloalkenes because we have a cyclo, and then you'll see this is a triple bond. This is how we draw a triple bond. That's how we draw a double bond. They will always be shown to you, so it stands out. So the naming rules are going to change slightly. In some ways, they become easier. And they're called unsaturated because they do not have the maximum number of hydrogens anymore. Yeah, there's our joke that the world is diverse to chemists because it's made up of all kinds of people. This picture here is my attempt, there's my blank paper, to explain like what's going on with a double bond. So what's happening with single bonds, and you don't need to write this down at all. You can just kind of get an appreciation. But do you guys remember we talked about SPDFs, orbitals? And p orbitals are these figure eights, and s's are just little balls. And so that's what this is trying to show, is this is an s orbital. And what happens when you make a bond is you get an overlap of orbitals. So again, this is more than you need, but it does help some students to understand how things are going to be happening, and something that's really key that we get into here. And the bond overlap is orbitals. So s orbitals and p orbitals. We're not going to actually see d's and f's because we're dealing with just carbon and hydrogen. So what happens when you're dealing with single bonds is that's pretty simple. You're just getting, like we have a carbon to a carbon, and you're just getting, these are p orbitals overlapping. And so we get an overlap, and that's a single bond. So for a single bond, so saturated hydrocarbon, the overlap is always in between the nuclei or in between the atoms. But what happens when we get to a double bond, so there's my carbons are right there, that the p orbitals, so remember p orbitals, you had x, y, and z. So you get this overlap in between, which is along the x-axis. And then remember these guys, that the p orbitals that were along the y-axis. So what happens in a double bond is they overlap, and you can draw them like with purple, is they make this weird overlap above and below. So this purple thing that I'm drawing here that's like a donut, that's one bond. Remember, electrons are really funky. They're working as vibrational potential, and this is one bond. And so this is a double bond. This is really what a double bond looks like. What a triple bond looks like is you'll have an overlap in between the carbons, overlap above and below the carbons, and an overlap in front and behind the carbons. That's what this picture is trying to show. What I'm trying to get at with this is single bonds rotate freely. And so it goes back to our study set on some of the pictures where we're showing the zigzags. Like you could draw 7 carbons like that. You could draw 7 carbons like this. They start zigzagging and stuff. But when you get to a double bond, there's no rotation. This donut like makes it stiff. And so it fixes it into a certain shape. And that ends up being actually really important. It ends up being something that we get into in nutrition or in Chem 106. So like for Philip next week, when we get into lipids, so the MUFAs and the PUFAs. So the word unsaturated, you've probably all heard of before, which is the unsaturated fats. So unsaturated fatty acids, and they're called unsaturated fatty acids because they have a double bond. Now, another thing about this unsaturation, because so way back in the 70s, in the 60s and 70s, they were saying they decided saturated fats. It was when they started, I guess it was in the 70s, when they started doing heart surgery and actually going in because people were getting clogged arteries and they were pulling out these clogs from the arteries. And then that's when the first heart surgeries were, was in the 70s. And they would analyze them and they were always filled up with saturated fats. So saturated fats are all single bonds, and saturated means they start stacking up. They do this zigzag and they just stack up and they make a clot. So that's the thing that happens with these single bonds is they stack and they clot. And so saturated fats come from animal sources and they just start stacking up, and cholesterol gets attracted to this and stacks up really nicely with them, and we get this really gummy thing that, and if it goes to your brain, you get a stroke. And that's like happening in 30-year-olds now because our diet's so crappy. So I'm supposed to live longer than all of you because I was brought up before all the processing of food and stuff. The thing that's really cool is our body heals itself. And so you can change now and heal yourself and heal everybody in your family. So what happens with the double bond though, is they said, okay, double bonds are great because it's gonna change the angle, and we're gonna get into bond angles here in a moment. But one of the problems that they didn't realize, one, the taste is different, but this is like a circus act. So mom and dad, you're holding like the kids in between in a single bond. These are electrons here. Remember electrons? And they're really safe. They're held in between those carbons. They're safe. Nothing's going to happen to them. So if you've been a mom, right? Kids like to be right there between mom and dad or between two people. We all like that. We want to be the monkey in the middle. What's happening here, this is like the circus act. These electrons are up above or down below. They're like out there, and they become really susceptible to damage. That electron can get knocked off. And when you lose an electron, oh, does anybody remember what we call it when you lose an electron? Philip's thinking.
Redox.
You're on the right track.
Redox.
Which one? Which one is it?
Reduce.
No, you almost had,
Oxidize.
it's Leo. It's Leo. Losing electrons oxidized. But I'm going to give it to you though, Philip. So if you lose an electron, we're oxidized. And yeah, and you make a free radical. And that free radical is miserable. It's got an unpaired electron. So again, I'm really missing the board because I totally forgot that I go on and on about this because this is one of my passions. And I don't know how you can understand nutrition without taking a little bit of chemistry so you can understand this. But these guys become free radicals. And it's anytime we see these double bonds, and these double bonds are in unsaturated fatty acids. And it's because of how a double bond is that the overlap is above and below, as well as in between. But the ones in between, they don't get oxidized. And so anything that has a double bond, if you go, there's four things that cause this. And the biggest one is high heat. And so the problem is oils. When we cook with oils, the heat is always going to be much higher than if you're cooking with water. Water doesn't have double bonds, so you don't have the problem. And so when you're cooking with any of these oils, you get these double bonds, you get this electrons get knocked off. And yeah. Jeremy was in my class last term, so he heard me go on about this. So high heat is one thing. Light, so photons is another thing. And so photons, I saw my clock and it's 9:54 at night, and I'm like, oh my God, I went way over, and you guys are still here, but it's because I'm in a different time zone. Totally forgot it for a moment. So light or photons will knock these out, and so most people, when they buy oil, most oils are sold in clear bottles. And so that's one of the things, like olive oils and the more high-priced oils. All oils are bad. All oils are going to be rancid by the time you get it. But if you think about McDonald's, right, when they're cooking the French fries, or Burger King, wherever you want to be, those things are getting exposed to the light, right? We have those huge lights all around them, or the pepperoni on your pizzas that you're making all day long, Philip, and the high heat that we're putting them in. Right, the high heat of those ovens, it's only for 2 minutes, but it's like those ovens are at like 500 degrees, right? The pizza ovens, or the deep fryers. You know, deep frying wasn't done anywhere. That's like an American invention, and it's like one of the saddest things that people wanted to replicate us. Oxygen. So the air that we breathe, oxygen is like the greediest thing. It steals these electrons whenever it can. Yeah, and the other one, which is kind of funky, is a lot of the metals. So like iron, copper, and a lot of these. So there are some people who are like obsessed with this, and they're like, you can't cook with a cast iron skillet, blah, blah, blah. I have a cast iron skillet. My mom actually has two. One's my grandma's skillet. It actually might be my great grandma, who I never knew, but there's certain things I make in it. It's the idea is you shouldn't do it all the time. But it is one of the reasons why women don't actually tend to have heart attacks until after menopause, because our iron levels are naturally lower because of the monthly cleansing, our menstrual periods. And then after menopause, your iron levels will go up, and women will start to have heart attack rates almost equivalent to men. Anyway, we can go on and on. It's been hours. All right, let's go back to this. I didn't even get to do some of the fun stuff. The molecular formulas, when you make a double bond, you lose 2 hydrogens. So what's the molecular formula going to be for if you have X number of carbons, how many hydrogens are you going to have? Well, normally we double and add 2, but we no longer add the 2. So there's still the 2 at the end extra, but now we lost 2 somewhere in the middle around the double bond. So that's going to be the molecular formula for alkene. Anybody want to try for what the molecular formula would be for an alkyne? So if you have X number of carbons, how many hydrogens?
H2X plus 2.
Almost. But they're going to lose 2 more, so they're going to actually be minus 2. So every extra bond, you lose 2. So this one lost the plus 2, and then this loses 2 more. So that's for the alkynes. And again, that's the generic formula. For bond angles, anybody want to take a gander? Actually, let's the triple bond. You can only then have 1 more bond on the carbons. There's 4 total bonds. So what's that bond angle going to be for the alkynes? It's just how it's drawn. And that's where it's going to get funky when we draw these. This is linear, 180 degrees. I'm fairly certain there are no triple bonds in nature. Man has made triple bonds. They're extremely reactive. With that said, I think last year I was Googling something and I found some weird exception to that, but I'm not sure it was real. All right, with a double bond, if you think about it, you draw the carbons. Carbons make 4 bonds. That is a rule. It's like a law. Of course, every law gets broken in chemistry, but so this carbon has a double bond and then it's going to have 2 more. That means there's 3 things around it. So this is the planar triangle or trigonal planar. Some teachers call it, it doesn't matter to me which way you call it, 120 degrees. And so our bond angles have changed. This is actually going to make our pictures look different. This is one of the beauties of drawing with zigzags, is you see more the angles that are happening. And when we draw it with the carbons, we don't see those angles as well. Now, with that said, when I ask you to draw them, do it the way you're most comfortable with. You will see ones that both ways drawn that you'll have to name. So let's go ahead and walk through these together. And I'll draw them both ways. You don't have to. So for butene, we have 4. And then this number, we're going to see a number now. And that number has to tell us the ending changes. So the but is here in the middle. That tells us we have our 4 carbons. And then the ene means I have a double bond. And that double bond is at number 1. So double and triple bonds are always between 2 numbers. We always put the lower number. So this 1 would mean it's from 1 to 2. And that's what our picture would look like, 1 butene. If you drew the carbons, you draw your 4 carbons, and then at number 1, you'll put your double bond. And then if you draw the carbons, you have to draw your hydrogens. So just be careful, because at number 1, you lost the hydrogen because of the double bond. At number 2, we only need 1 hydrogen. And then at number 3 and at number 4. And that's why it's called unsaturated, because we've lost hydrogens. All right. 2-butyne, if we draw the carbons, and actually it's probably worth it. It's probably why I gave you enough space on these. This would mean the triple bond is between 2 and 3. So we always give, this number goes with the I, Y, and E, and it's saying we have a triple bond between 2 and 3. Now we fill in our hydrogens. At number 1, we need 3 hydrogens. But at number 2, it's already, there's no room. At number 3, there's no room. So at a triple bond, there's no hydrogens. And that's why it comes out straight across. And that's why, if you're going to draw this, this is what it looks like in the zigzags. So this is carbon 1, this is carbon 2, this is carbon 3, and that is carbon 4. It's a straight line on each side of the triple bond also. So like here on this one, this would be 1, 2, 3, 4, 5, 6. So a lot of students who love doing the zigzags, when they get to a triple bond, they go back to drawing carbons, which is perfectly fine. You can do that. All right, so the next one. So if you want to try and draw it, let me give you a moment. Take a deep breath. Actually, I'm going to go ahead and pause. And so you can take a 5-minute break, or you can try drawing these. And yeah. All right, let's just go ahead and go through it. So I'm going to, again, these drawings, I'll show you 2 different ways. So if it's a YNE and you're going to draw it with the lines, you have to have on each side of your triple bond, it's going to be straight. So this would be 1, 2, 3, 4, and then it starts zigzagging. So there's 5, 6, 7.
Wow.
And then at number 4, we want to do our tert-butyl. So we're going to point it down. That's the chicken feet. That's going to point down like that. All right. This is, just be careful, right? It's cyclohexene. So it's still just the hexagon, which gets a double bond. You can put the double bond anywhere you want. However, the double bond is number 1, 2. So the double bond always gets preference. And in a cyclo, it's always at number 1. So we'll call this 1, 2, and that will make this 3, and isopropyl. You could have also gone the other way. There's my isopropyl. All right. So I threw a bunch of curveballs at you at this, but it's good for you to practice or to take a break. The double bonds and triple bonds in our class, cannot be on the side group. They have to be the main part. So on this one, we're going to do 1, 2, 3. It is no longer necessarily the longest chain. It's the longest chain that contains the double or triple bond, or in this case, we have 2 of them, 4, 5, 6. And this should have been connected there. I think yours didn't have the line. Yeah, again, I didn't like look through these to make sure everything lined up. So this was not necessarily our longest chain, but there it is. This side group over here, that side group is 1, 2, 3, 4. That is a sec-butyl at number 3. So we'd say 3 sec-butyl. And now we have double bonds 2 different times. We have a double bond at number 1 and a double bond at 5. So we have to say we have 2 of them. They each get a number, and they have to have the lower number of the double bond number. So it's a 1,5 hexa diene. So the di is before the ene, because we have 2 double bonds, not 2 hexas. So you don't want to say 1,5 dihexaene, because we don't have 2 6 carbons, we have 2 enes. So you can see where the jokes are going to come from, dienes. All right, this next one, 6 carbons, just a 6 straight across. And my triple bonds at number 3, so 3 hex, and then YNE. So triple bond is YNE, double bond is ENE. When you have a di or a triene, we put the A there so that you don't run 2 consonants together. Those are all minor things. All right, this should have had a line connecting them. Again, some of my lines disappeared. Maybe yours is there. And I don't think I made any changes to the notes, but I printed these notes last year, and so I'm pretty sure if I'm ever doing the wrong notes, somebody please let me know before I go through like a whole page. The double bond has to be 1, 2, and you want a number towards the side group. So this would be 1, 2, 3, 4. So the side group, we wanted to have the lowest number possible, but the double bond or triple bond, they take preference. So it's no longer, this was a question a lot of you were asking me with the worksheet tonight. The preference now becomes the double and triple bond. They have to have the lowest number. So whatever side they're closer to. The double and triple bond do not have to be at number 1, but they have to be they do have to be at number 1 in a cyclo. So this is a cyclohexene. We don't put a number for it because the cyclo tells us the ene is at number 1. And then this is a tert-butyl. This is saying I have a carbon with 3 CH3s around it. So it's saying I have a carbon, and then there's a CH3, a CH3, and a CH3. So that's what that looks like. And so it's the chicken foot thing. So for tert-butyl. Cyclohexene. All right. Double bond, I'm going to number for both of these. The double bond means I'm going to start numbering from that direction. So 1, 2, 3, 4, 5, 6, 7, 8. And this one is the same, 1, 2, 3, 4, 5, 6, 7, 8. Again, if you can find those erasable colored pens, those things are amazing. So being able to erase and then to do color. So these are, this has just that 1 double bond there at 3, so 3 octene. There is an extra piece to both of these. I'm trying to decide if I want to go there tonight or do it on Wednesday. All right, this is an octadiene. So we say octa before the diene. So again, the di tells me there's 2 double bonds. The double bonds are at 1 and at 3. So 1, 3 octadiene. Yeah, I guess I'm going to talk about it tonight. All right, let's go straight across. These are my nicer. Double bond takes preference, so 1, 2, 3, 4, 5, and then I have methyls, so 2,4-dimethyl. And then we need the numbers, so 2-pentene. So just ENE, and I mentioned this last week. I'm just underlining it to emphasize, you don't have to underline, that your handwriting needs to be where I can tell it says ENE. All right, this one here, that's my 1, 2, and there's the 3. So 3-methyl and cyclohexene. Something else I wanted to mention, nobody's asked because you're all being so polite, but your celebration is in like 2 weeks and 2 days. It is going to be all show your work. 2 weeks from today, we actually do a review. So the printout you'll have for that day will be like 4 pages. It's actually an old exam that we'll work through together. And so when we do that, the midterm or the celebration, it will be during this time. And it will just show up on Blackboard, and you'll print it out or look at it and write it out on a piece of paper, and you'll be fine. So we gotta do this one. These are double bonds, and they are at the ends either way. My longest chain is straight across. So if I start here, 1, 2, 3, I run into a side group at number 3. If I start here, it's 1, 2, 3. So my question to you is, where do I put my number 1, on the left or right, and why?
Would it be the right because you have the
Why? Go ahead.
Because you have the isopropyl.
It is, Vincent. So isopropyl, this is an isopropyl, and this is a methyl. And so it was a question again that some people asked me last week, that, why was I putting the I or the M? It helps us alphabetically. This is, again, very rare that it happens, but if it is the double bond that takes preference of which side you start numbering from. But since my double bonds are at the end, anyway, there we go. So this is a heptadiene. My double bond is at 1. Oh, you know what? It's not hepta. It's octa. So hopefully you laugh at yourself when you number like I just did. There's 7 and there's 8. So that was octadiene. I apologize. So 7, 1 and 7 are my numbers. So 1, 7, octadiene. And so way out here, we do a 3-isopropyl. These names are crazy. And I'll just put an arrow that this is going to go up in here. 6-methyl. So commas between numbers, dashes between numbers and words. YL is if it's a side group, so isopropyl or methyl. But our main chain, the octa, it gets an ene or an ine ending. Any questions? That is what the study says. Move that. And again, it takes practice. It was something Allie was talking about earlier, and I actually liked her comments. Sometimes it's really nice to just listen. You guys have a huge advantage since this is being recorded, that you can always go back and watch the recording. And so she said she likes to sometimes just listen as I'm going through it the first time, and then she'll go back. Or you can do it the opposite. You can sit there and furiously copy everything as I go through it. And then it is really nice to go back and listen to the videos, because sometimes as you're furiously writing it down, you're missing a lot of the words that I'm saying. All right, let's go ahead to the next page. So we're going to do Cistrans Isomers. And you've probably all heard at least of trans, because again, it's trans fats. But you can't have trans without, there's also the possibility of cis. These pictures here show it. This is trans. Trans, you keep the zigzag, and cis actually shows correctly what happens at double bonds. In nature, pretty much all double bonds are cis. Cis is the natural way. I used to say all are cis, but of course somebody has found something that is trans. So let's just do the simple one with 2-butene. This is probably one of the hardest things we do initially when we see it, and it just like everything else takes practice. So like today on the study set, the most common asked question is those isomer questions. The hardest part for a lot of students, the study set for Wednesday, your class Wednesday, is the cis-trans, but it just takes us to do practice. All right, so butene is 4 carbons, and I'm going to draw this doing zigzags and drawing the carbons. So let's do it drawing the carbons first. So if you draw 4 carbons, the double bond's in the middle. So the ones on the outside, they have their 3 hydrogens. Now the ones in the middle each just have 1 hydrogen. And so the reason there's 2 different ways is I could draw it where I put both hydrogens pointing up, the hydrogen on 2 and the hydrogen on 3, or I can draw it where I put one pointing up and one pointing down. And this goes back to where I went off, not actually on a tangent, but it might have felt like a tangent a half hour ago. Double bonds do not rotate. And this, so just write a thing, double bonds do not rotate. They are stuck in position. So these hydrogens are either both pointing up or one's pointing up and one's pointing down. So you can't rotate them. When we have the zigzags, single bonds, we can rotate them all different ways, but these get stuck. This is cis. So sisters, they're pointing in the same direction. And trans is like the Transcontinental Railroad, which I get to take this weekend, across the country. So trans means across from. How this looks in the zigzag is what happens at the double bond in a trans is you come in one direction and you go across. And so trans are really simple to draw. They're just zigzags. So trans is going to do a zigzag. And that means that they stack up and they cause clots. These guys are a double whammy because they have a double bond, so they go oxidize and they stack up. For a cis, what happens is you come in, you hit the double bond, and then you go out in the same direction you came in. And so you get what my nutrition teacher called a kink. So these guys are very kinky. They have a bend, a kink or a bend. So they do not stack. They are fluid. And so oils are liquids, and things trans, that's where we took margarine. Margarine is trans fats, and it's a solid, and that's because it could stack up. And so these were fluid and flowing and stuff. All right, we're going to do practice with this on this page. And so what are we doing with this? We are first, for these guys here, this is why it is nice to have the notes printed so you can write on them. We're just looking to see if it's cis-trans. So it's this really long, wordy, awkward way of the full definition. C is not cis-trans. So what has to happen is it has to have on each side of the double bond. I'm going to attempt to write my definition out. So on each side of the double bond, you have to have different groups. Not different, different groups, pieces sticking off of them. Meaning these have to be different from each other. This fluorine, they can't be the same thing. This can do cis-trans. This is trans. And that is, I have a hydrogen here and I have a hydrogen trans across from it. That was not a really good way of, my brain understood it. Here, am I comparing this fluorine to this fluorine or this one to that one? We don't know. All right, D is neither. Because again, when we look at this CH3, am I comparing to this one or am I comparing to that one? So these two on this side of the double bond, these have to be different. On this side of the double bond, that side's okay, but my right side's not. I stopped recording myself again. So people watching the video don't get to see me making all these weird faces. I had a student last year who'd been with me for several terms, and he said that. He's like, now that I see you on video, I get to see, because when I'm up in front of the classroom, you can't see me making all the faces I make at myself. All right, this one is cis. Again, it's tedious. It takes practice to see it, but we come in this direction, and then we go out in that direction. So it's 1, 2, 3, 4, 5. So we would call it 2-pentene, because my double bond's at number 2, and to have the full name, we would write cis in front of it. So this is the full name. So before we do these, we're going to go back a page, because there were some cistrans on the previous page, and I want them complete in your notes. So when you go back and look, so we're going to go back. And triple bonds can never, ever be cistrans, because they're straight across. There's nothing going on there. They're straight across. You need the double bond to be in the middle. So you will never, ever have cistrans when it's at the end, because this has 2 hydrogens. So if there's 2 hydrogens, if you're at the end, that's the only way you can have that. You can't do cistrans. So it's when it's in the middle, like this guy. So these are both trans. And the trans would go in front of the name. We don't do it with this one because it's at the ends. We don't do it with the cyclos. We don't do it with the triple bonds. And on this one, B, we don't do it with. So there we go. Another bonus opportunity. Anybody see why on this one? It's really tedious to explain why that is not cistrans. I did name it.
Is it because of the dimethyl?
So yes and no. It depends which methyls you're talking about. So when in the name 2 and 4 were the methyls, but in determining cistrans, I'm looking here at carbon number 2. So the left side of my double bond, it has a methyl and another methyl. It has 2 of the same thing. My right side has a hydrogen and then a carbon. It has different things, but on the left side, they're the same. So it's not cistrans. It's really tedious explanation. Within the next 2 weeks, like here, number 1, we don't do cistrans, so it doesn't matter because of the hydrogens. All right, I'm going back. Here, there needs to be a line around these carbons hooking up. So I'm going to pause again, give you 5 minutes. You can either take a break or you can try doing these. Or down here, you can try making sketches. And I'm just going to stop recording for a couple minutes. We'll resume. All right. So we're numbering and naming. Our longest chain is going to zigzag. These guys are going to be my side groups. So the double bond needs the lowest number possible. So I'm going to start there. 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's a 4-nonene. So remember, you do need a number, ENE, for the double bond. The 4 says the double bond is at 4 to 5. And then we have to say these extra pieces. So 4, 5, dimethyl. And then there is one more piece, which is, anybody?
Trans.
It is trans. It is zigzagging from top to bottom. So when it starts at top and goes to bottom, that would be trans, or vice versa. Cis would, we're going to do a cis here. So I'm going to draw it with carbons. You can also do zigzags. Some people like the zigzags until we run into cis, because this is a little bit harder to do. So you have 6 carbons, comes from the hex. Ene means number 2 is my ene, so 2 to 3. Cis means my hydrogens are pointing the same way. You can just do 6, or sometimes I like to write them in when I'm teaching. So this is 1, 2, 3, and then at 4 we would have a methyl. And then I have to fill in my other hydrogens either with lines. No more lines there at 2 and 3. If you do a zigzag, how many did I get? 1, 2, 3, 4, 5, 6. And then at 4 you would have a methyl. That's kind of our idea there. You can zigzag more, but you have to show that kink that happens at number 2. All right, with these, you can always make a quick sketch. 1, 2, 3, 4, 5, double bonds at 2 to 3, and then we're putting a methyl. The answer is no. It has to do with here at number 2. Those are both methyl groups. So which way am I going, like across like this, or am I coming down? Doesn't work. Number 1s are always no. And that is because at that number 1 carbon, if we drew our 6, there are 2 hydrogens. So they're 2 of the same. All right, butane is no, because it's a triple bond. So triple bonds are no. No, because it's at carbon number 1. And then this one does work. So you could do zigzags, 2, 3, and then we have methyls at 3 and 4, so that would be trans. Again, you can draw it 1, 2, 3, 4, 5, 6, triple bonds at 3, a methyl above, a methyl below. The reason why it's yes is if we look at this carbon number 3, we have a 2 carbon group and we have a 1 carbon group. We have different number of carbons. Carbon 1, 2 carbon. Same over here. We have a 2 carbon group and a 1 carbon group. So a different number of carbons. So this is yes. And this is a small piece, but it does help as we go through it. You're usually going to see it where it's giving it to you and it's asking you to draw them out. Let's go ahead and go through these, and we're almost done. All right, so 2-hexene. So again, you can draw zigzags. So at 2 to 3, we have our double bond. And then at number 4, so 1, 2, 3, 4, we're going to do a sec-butyl. So sec-butyl is 1, 2, 3, 4, 4 like that. You can also draw your carbons 1, 2, 3, 4, 5, 6, double bond. In this case, just make a sketch. And the problem in both cases is our longest chain needs to be 1, 2, 3, 4, 5, 6, 7. So you can do it like this. It is a heptene. The double bond is still at number 2. We have a methyl and we have an ethyl. So the ethyl is at number 4. So 4 ethyl, 5 methyl. Does anybody see there's one more piece? To get full credit, you would have to put one more thing there. So it's 4 ethyl, 5 methyl, 2 heptene. We go at the very beginning, and you get a choice because the gnomes didn't tell us. It is a double bond, and it's in the middle. It's a cis-trans. It doesn't have to be smack in the middle. It just means it's not at the end. So you can pick. If mine's trans, because that's how I drew it, but you could draw it as a cis. The cis or trans is always at the very beginning of the full name. It is not hyphenated. There's no dash, there's no comma, and it's technically italic. That's more detail than you need, but that's why up here it's shown correctly. So again, it's an italic, and it's just like a forethought. Hey, by the way, like technically here, that's not going to be the mistake that there is no dash. But if we wanted to draw it with zigzags, 3, 4, so there's 1, 2, 3, 4, 5. We're showing the cis, and then we put a methyl at number 1, and then a methyl at number 5, and then at number 4 they put an ethyl. So this is what it's going to look like. I think these are really hard to watch somebody else do them, but at least you'll get a name and you can go back and look at them and always come and ask. This would be our 2-pentene, a methyl, and an ethyl. So sometimes these are easier to do for some people to draw the carbons out. Not that. So our longest chain is much longer. 1, 2, 3, 4, 5, 6, 7. If we do it this way, 1, 2, 3, 4, 5, 6, 7. So heptene, double bonds at 3 now. It is still 6, and we just have this ethyl side group. So 5 ethyl, 3 heptene, and we do want to keep it as cis because it is a double bond that is not at the end. So we must have the ability to do the cis trans. All right. Something I just want to mention, cyclohexane, cyclopentane. It's actually cyclopentane. You can do cis trans with that. I'm just not going to go there because in biological chemistry, it's not important at all. But in case for those of you who really get into this or go to a higher level, this though is cyclohexene, which we don't do cis trans. So we draw our hexagon, and they're saying the double bond's at 3, and the methyls. Well, they named it wrong. So the double bond has to be at 1, 2. You would not put a number with it. And these are either going to be at 3, 3 or 4, 4, or yeah. They're either going to be a 3, 3 or a 4, 4. It kind of depends. Can they be at 4, 4? Yeah. It depends how you interpret the incorrect name. So I got 3, 3 dimethyl cyclohexene. We don't show the number because it always has to be at number 1. And all right.
On a test, if we include
Go
the
ahead.
number, on a test, if we do include the number, is it wrong, or will it be marked wrong?
Yeah, there's part credit, Ezra. Obviously, like for the worksheets, because there's the naming. There's so much little detail. It always actually amazes me if somebody loses not even a half a point anywhere on the naming page. So it would not be completely wrong. That's why we're not doing multiple choice. Yeah. So the next page, we're going to just look at real briefly. This was just, and you can look at on your own. You guys are going to be doing 2 class presentations. Your bigger one is you're going to pick a organic molecule that you're going to research and write about. And you have to actually, in that one, you have to have 2 scientific studies that you look at. But the double bonds, this is where we start getting into some that are interesting. Pheromones, which are what insects, how they attract other insects. This middle one, though, is pretty cool because it's the use of cis trans. Actually, just real quick, looking at this, these are cis. They come in and then they go out. So this one is cis, but this one is trans. So this one, we're coming in and then we're going out. They're both up above. But this one, when we come into this double bond, it's coming in from below and then going out from above. It's kind of funky. Yeah, and then it has an OH over here. Double bond's more important, but the OH is too. This is really cool because this is what's going on in our eyes. That light changes the double bond from a cis to a trans, and that changes how we perceive light and color, which is pretty cool. The terpenes, the big place you see terpenes right now is with cannabis. So again, there's over 120 terpenes in cannabis, but there's actually like thousands, millions of terpenes out there in nature. So like lemon oil, rose oil, menthol, ginger bar, and beta carotene. So the carotenoids or the tocopherols, vitamin E and stuff. Anyway, it was just showing all the different, some cool different molecules. Just send there, and I will hang around. So if you have questions on your worksheet or other stuff, so don't forget to turn in your worksheet before midnight, and I'll see you on Wednesday.